Welcome to Organic Reaction Mechanism, Part 3, SN2 Reaction Mechanism. When methyl bromide is reacted with aqueous KOH, we get methanol as the final product. This reaction goes by biomolecular nucleophilic substitution reaction. Mechanism-wise, we write the details of CH3Br and attack of OH is shown from the backside. This carbon has partial positive charge, bromine has partial negative charge. If we bring OH minus from the front side to attack on carbon, this attack is hindered by repulsion between the negative charge of bromine and negative charge of OH minus. CBr bond has plus and minus charge, so this bond is having a dipole, and this OH is a negative ion. So there is ion dipole repulsion, and because of this repulsion, the attack from the front side is not possible. From the back side, the size of hydrogen is small, so there is no steric hindrance, and it helps OH minus to easily have an access to this carbon and make a bond with this carbon. As the electron density is transferred toward this carbon, we show that there is a bond generation between OH and C. At the same time, the bond between carbon and bromine will start breaking down. So we show an intermediate where OH is half bonded to carbon and the bond between carbon and bromine is half broken. Finally, the complete bond formation takes place. Bromine leaves the system and we get this product. This is known as SN2 reaction mechanism. This mechanism can be described in 3 paragraphs. When substitution reaction is carried out with the help of nucleophile, it is called as nucleophilic substitution reaction. Mechanism-wise, alkaline hydrolysis of methyl bromide takes place by SN2 reaction mechanism, leading to formation of methanol. It is one-step reaction. Hydroxyl ion cannot attack from the front side due to ion dipole repulsion. Therefore, attack takes place from the back side. An intermediate is formed with pentavalent carbon. SN1 reaction mechanism. Alkaline hydrolysis of tertiary butyl bromide takes place by SN1 reaction mechanism, leading to formation of tertiary butyl alcohol. It is a two-step reaction. In the first step, CBr bond breaks to form tertiary butyl carbonium ion, and this carbonium ion is stable due to electron donating inductive effect, which is later on attacked by OH minus in the second step. So we have tertiary butyl bromide and we are reacting with OH minus. Now in this mechanism what we do is OH minus has no role to play in the first step because bromine has minus charge. So from the front side, when OH tries to access the molecule, there will be a repulsion. From the back side, if you consider the size of methyl group is too large and this steric hindrance does not allow OH minus to attack from the back side. So neither front side nor back side attack is possible in this substrate. On heating, carbon-bromine bond starts breaking down slowly. We write an intermediate where half broken bond is shown, and finally bromine leaves the system to give us a carbonium ion. The geometry changes from tetrahedral to trigonal planar. This carbonium is a planar structure, flat surface like structure with a positive charge. Now on this carbonium, OH minus will attack. Since it is a flat surface, attack from both the side is possible, from the front side as well as back side. So we show both the attacks. OH minus when attacks from this side, methyl will move to the opposite directions. So they have moved to the opposite direction when OH comes from this side. The intermediate shows half formed bond, and now when the bond is completely formed, we get this product. Similarly, from the other side, when OH attacks, methyl will move to the opposite direction. So OH is coming from this side, methyl have moved to the opposite direction, and we get this product through the intermediate.
Sets of elimination. During an elimination reaction, more substituted alkene is favored as the major product. This is the statement of sets of elimination. This is the example of sets of elimination where when you react 2-bromo-3-methyl butane with sodium ethoxide in ethanol, we get
2-methyl butene as the major product. In order to write the mechanism, we show the detailed structure of 2-bromo-3-methyl butane. Bromine will be lost from this carbon. It has two neighbors, and both of them have hydrogen, so either this hydrogen will be removed or this hydrogen will be removed. We have to show that removal of this hydrogen is favored, and we get more substituted alkene as the major product. So we have our base with us, ethoxide ion. It takes out this hydrogen. We write the intermediate where base is trying to remove the hydrogen. So this is the bond between oxygen and hydrogen, which is half formed. This bond will start breaking down, so this is shown by broken lines. The single bond is in the process of becoming a double bond. So we show that dotted line, and bromine is ready to leave the system after completion of the double bond. So we show it again by we get this product. When ethoxide ion tries to remove the hydrogen in the intermediate, we notice that this hydrogen is surrounded by other groups. This hydrogen is easily accessible to the base. This hydrogen is not easily accessible. However, the steric hindrance between the base and the groups of substrate is not very strong. One thing can be noted is the transition state matches with more stable alkene and does not have much steric repulsion. Therefore, we get a stable alkene as the major product, and this product is formed in more amount. However, there is a possibility of formation of the other product where base removes this hydrogen and we draw the intermediate. We don't see any steric hindrance because this is away from all other groups of the molecule. But this transition state is matching with less stable alkene. Therefore, we get this product in less amount. Hofmann elimination, an elimination that gives the less substituted product in excess is said to follow the Hofmann elimination. When a bulky base like sodium tertiary butoxide is heated with 2-bromo-3-methyl butane, 3-methyl-1-butene is formed as a major product. We have taken the same alkyl halide which we have considered in the sets of elimination, but this time the base we are using is a bulky one. Earlier we used sodium ethoxide, now we are using sodium tertiary butoxide. When it is removing the hydrogen, when we write the intermediate of removal of hydrogen, we can notice that these bulky groups are close to each other and there is a strong steric repulsion between them. Thermodynamically, this transition state is unstable, although it is matching with more stable alkene. Since it is highly unstable, it will not be formed in more amount, and the product which we are going to get will be in lesser percentage. If we withdraw the hydrogen from other side and draw the intermediate, the bulky group does not have any kind of steric repulsion with the rest of the molecule. It will form less stable alkene, but the transition state itself is more stable. So when we compare these two transition states, This TS is less stable because it has a steric repulsion, and this transition state is more stable because it does not have a steric repulsion. Although the alkene which will be produced from this transition state will be less stable itself because it is a terminal alkene. We know that non-terminal alkenes, non-terminal double bonds are more stable and terminal double bonds are less stable. So this will be the minor product and this will be the major product. Pinacol rearrangement. Pinacol rearrangement where a dihydroxy system goes into a ketone. After rearrangement, we have H plus ion in the system and our dihydroxy system. We give the lone pair of oxygen to H plus ion to make this intermediate, where OH is protonated to form OH twice with positive charge. The bond between oxygen and carbon breaks down and loss of water takes place, and it also gives us a carbonium ion. Migration of this methyl to this carbonium is supported by lone pair donation of oxygen. So oxygen donates the lone pair, we make a bond and break away methyl and give it to the neighboring carbonium. We get this kind of rearranged system where in place of two methyls on the right hand side, we have now three methyls because one methyl has come after migration from the neighboring position. Oxygen has given the lone pair of electrons, so oxygen gets positive charge and a double bond is there because of electron donation. Later on, H plus ion is lost with the help of bisulfate ion and we get the final product as ketone. Beckmann rearrangement. Formation of substituted amides from oximes in the presence of dilute acid is called as Beckmann rearrangement. The mechanism in the presence of sulfuric acid, so we have H plus ion, we give lone pair to H plus ion, we protonate our OH, this OH is lost from nitrogen. At the same time, methyl is migrating to this nitrogen with its electron. This migration leads to a product where methyl is now present on nitrogen. Water is lost from nitrogen, and because of migration of methyl, this carbon has positive charge. Water attacks with lone pair and we get an intermediate which has enolic functionality. This enol will tautomerize. Lone pair of oxygen is given to the neighboring carbon. Bond opens up of bonds open up towards hydrogen. We get the next structure. Finally, loss of this hydrogen gives us amide. This was the third and the last part of organic reaction mechanism.